Okay, good morning. Doing this video here to go over the word problem from 6C and then the first page of 6C part 2. Try to go through this as fast as I can. So I want to sort of apply what was going on yesterday with the 6C notes. So let's say, a teacher wanted to create a curve formula for a test, okay? And we want to curve a 40% to a 70%, a 50 to a 75, a 70 to an 80, and a 90 to a 95 or something like that. Okay, so what we'll do is we'll make our table again. 40 becomes a 70, a 50% becomes a 75%, a 70% becomes an 80%, and then a 90 becomes a 95. Okay, so what we want to do is, if we just know that this curves to this, and this curves to this, and this curves to this, and this curves to this, well, what we're trying to do, what we're trying to accomplish here is we're trying to take these 4 data points and create a function that fits all those data points, where we can take any grade that we want and curve it accordingly that sort of fits this formula the best. Okay, that's why we do this thing. All right, so we come over here to our calculator, and I'm going to clear this. So we'll make our table. So 40 goes to a 70, 50 goes to a 75. Trying to do this from memory here. 70 to an 80, and a 90 to a 95. All right, so we have this thing that kind of looks like this. I don't know if it's a perfect thing, but we're trying to find the equation of a line that kind of best fits through this right here, okay? And we're going to use a square root regression, okay? So I'm trying to get a line that kind of looks similar to the square root function that sort of goes through all that stuff, okay? We don't have to always use square root. We'll talk about a different type here in a minute, but for the sake of that, we're going to do the square root. So again, we'll come here and we'll go, our y1 tilde a plus b times the square root of x1. All right, and then we get the equation of our line right there. All right, so we get the equation of our line of best fit, our square root line of best fit that goes through this thing right here. All right, so what happens is we have 21.9 as our A, 7.4 as our B. And so we come here, and I'm just going to keep writing the notes on this page here. So, our Y is equal to 21.9 plus 7.4 root X. Okay, so now what we can do is we can go into this formula right here, plug in any X value that we want, and see, what the thing would curve up to. All right, so let's say hypothetically, even though we only have these 4 data points, if we look at the line of best fit, let's say somebody gets a 60 on a test, right? Well, we could go to our X value of 60. All right, and we see that point 60, 79.5. Okay, so when we plug this thing in here, we can say, okay, well, if you get a 60 on a test, it'll curve to a 79.5 in the grade book. We could also plug 60 in for this X right here, calculate the equation up. We'd also get 79.5 for our Y, okay? So what it is, it's sort of, in real life, you don't have perfect linear, functions like that are nice, smooth lines that have formulas, okay? In life, with science or math or statistical research or whatever, you have a bunch of data points, okay? And from those data points, you try to find the best fitting function line that goes through it. That way you can kind of create a formula that sort of matches the data. It's never going to be perfect, but, something that's sort of close enough to where we can kind of put a formula to it. All right, so that's sort of the essence of what we're doing. Now, let me say something here real quick. I didn't talk about this with my other classes, but let me talk about this now. Let's say hypothetically, we didn't want to do a root function through this. Let's say we wanted to do a linear function through this, a straight line, a linear function through that, okay? Well, we know a linear function is y equals mx plus b. So if we wanted to do a linear function through that, we could do this. y1 equals mx1 plus b. Oh, sorry. y1 tilde mx1 plus b. All right. And what that gives us, that's going to give us a linear function line of best fit that goes through that with a slope of 0.47 and a y-intercept of 50. Okay. So if we wanted to run, a best fitting line that was a straight line like that, okay, rather than a root looking type line right there, we could do that where, the equation of this line is y equals 0.47x plus 50.3 if you want to. Just depends on the shape of the data. It depends on the shape of the data, which is where we're going to go to next. So pause the video if you need to. Write down what you need to. I'm going to go on to part 2. All right, so coming on to part 2, we have all these numbers right here. I'm going to try to get them off to the side so where I can make my table here. So we have a candy store wants to give a discount based on the price of candy. So we'll go 1, 10%, 2, 14%, $5, 16%, $7, 17%, $15, 20%, $20, 25%. No, yeah, that's right. $25, 20%, $40, 12%. Okay. Now, looking at this data table right here, again, pause the video if you need to. I'm trying to go through this fast as I don't have a lot of space to store these videos in my hard drive. All right. So here we have this data, right? And again, if we wanted to do a root regression, we could do a root regression. y1 approximately equal to a plus b root x1. All right. And here we get our root line of best fit, okay? These square root functions always have sort of that shape, okay? So the square root function is always going to give you sort of that kind of shaped line right there that goes through these data points the best. Now, hopefully we probably see here that this thing does not go through these data points very well because these data points, they go up and they come back down. Okay, so there may be another type of function that fits this thing a little bit better. What kind of function would fit this thing better? Well, I think it would be a quadratic. Okay, so we can do a quadratic regression through these points rather than a root regression because these points look a lot closer to a quadratic function than a root function. So let's do a quadratic regression. How do we do that? Well, we know a quadratic is ax squared plus bx plus c. So let's go down there and do that, but instead of x, we just got to use x1. So we have ax1 squared plus bx1 plus c. So we have ax squared plus bx plus c. Now we have a quadratic regression that goes through this thing. It's much cleaner. And they give us an a b, and a c. So if we were to do a quadratic regression through these points, it would be negative 0.03 x squared plus 1.15 x plus 10.41. Okay, so that is kind of that right there. I'm going to go back and fill in the rest of these notes, and then we'll be done. Okay, so here, did we notice anything about the graph and the data points? Okay, not a good fit. Okay, because, you know, the shapes are not the same. The shapes are not the same. Okay, you know, our data points went up and down, and our, you know, our line of best fit, you know, was something kind of like that. Well, that doesn't work. Okay, so the best graph that fits the data was a quadratic. So our equation, we'll write, I'm going to write this down here, y1 approximately equal to ax1 squared plus bx1 plus c. The quadratic equation, I just wrote it on the thing a second ago on the graph. Hopefully you wrote it down. If not, if you don't see it, it's on the board behind the table in the front corner of the classroom. Okay, it's up on the board. And if we wanted to do a linear regression, we talked about that earlier, what we could do if we wanted to do a straight line, mx1 plus b there, and that should be a tilde symbol. Okay, so try that. Go ahead and try the problems on the back out. Hopefully this video is short and sweet and still gets to the point. If you have any questions, we'll be back tomorrow. We'll have an assignment over this tomorrow, and if we got to slow it down and reteach some things, we need to. But hopefully this is all pretty simple, and you guys can kind of sort of figure this out. So you guys take care. Have a good day, and hopefully this makes sense, and it's pretty simple for you. So thank you.